David was supposed to introduce me, but since he's not here, let me just say I'm awesome, and the talk will be great. Okay, so this is about pseudo-randomness from pseudorandomness from shrinkage, and this is joint work with Russell Impagliazzo and David Zuckerman. Okay, so so the main thing we'll talk about here is this connection between hardness versus randomness. I mean, so one of the central questions in complexity, like the two of the central questions are whether or not you can get circuit lower bounds, and the other question is whether or not randomness helps in computation. Okay, so these are the two, I mean, I guess in some sense these central questions. And by now we know that there's a strong link between the two. So usually one direction is, I mean, quite clear. If you have some kind of result or pseudorandom generator, then you immediately get a hardness result for that class of functions. But what's also surprising is that in fact there's a connection from in this forward direction. That is, if you have some hard functions, then you also have pseudorandom generators for that class of functions. And this has been studied a lot in the past. And what we really know, I mean, it has been very successful in complexity. And like two of the main results here are like unconditional. So you can get unconditional pseudorandom generators using this framework, using known lower bounds for complexity classes. And this was kind of this is from the work of, for example, you get PRGs for AC0. Okay? I guess you usually don't have this. This is due to Nissan from 91. Okay? And let me just define what a PRG, I mean, we'll go into formal definition later, but what's a PRG? So you have a class of functions, f from, let's say, n bits to, it's a Boolean function. And you have a generator g, which takes a short seed of length r and maps it to n bits. Okay? And we'll say g is a PRG for f with error epsilon if probability that f of x equals 1 when x is at random from the uniform distribution where all n bit strings is close to the probability that f evaluates to 1 when the input is chosen according to the generator. Okay, so the class of functions cannot distinguish the output of the generator from that of the truly uniform distribution, right? So we know like one of the first connections, kind of trade-offs between the two, was given in the work of Nissan, who used the known lower bounds for AC0 for parity to construct PRGs for AC0. Okay? And this also led to conditional PRGs. And here, kind of the main the celebrated result of Impagliazzo-Wigderson from, let's see, 0, 1, like in a long line of work ending with Nissan-Wigderson, Impagliazzo 0, 1, and so on, says that if there exist hard functions so this is an informal statement. What it says is that if there exist very hard functions, then P equals BPP. In other sense, in other words, randomness is not necessary for efficient computation. Okay. So this has been a very successful paradigm for connecting or devising PRGs from hard functions. But with great power comes limited applicability. In this case, that translates to saying that if you do not have very strong lower bounds, then these reductions don't give you anything. Okay. For instance, all of these reductions lose polynomial factors in them. And if your if your lower bound that you started with was itself some like cubic or quadratic lower bound, then they give you nothing. Okay. So what's the drawback of this? Is it's quantitatively weak. So for instance, let's say I have a class of functions for which I have only cubic or quadratic or n to the c lower bound, where c is some fixed constant. So we get no such reductions, and there is in fact a reason for this. So there are constructions which say that you cannot get such black box reductions from such small lower bounds. Okay. Worst case. Because in some sense PRG is itself an average case lower bound, right? So you can either talk about worst case or some kind of weak average case, but let's talk about worst case lower bounds. And this is kind of the status, and this is in some sense unavoidable. Basically, no black box. You cannot get black box reductions from hard functions to pseudorandom generators when your hard functions only have like such small lower bounds to begin with. Okay, and so what we'll study in this.
So how strong a lower bound do you need?
So basically, I mean, there are various restrictions. Like for instance, first of all, your complexity class needs to be powerful enough to compute majority, right. And on top of that, you also it depends on. But by and large, you cannot do it with, let's say, cubic or quadratic lower bound. You don't get anything. Maybe you'll get some small gains, but not much. Like this recent work of Umans, Shaltiel, etc. They did some get some gain, but it's not significant enough. Okay, so this is the big picture, and what we'll see in this work is basically that. So if your lower bound is proven by a specific technique, then in fact we can translate all the hardness into randomness. So this is, if you have hardness via shrinkage, so this implies PRGs. Okay, and effectively we'll recover all the hardness in the sense that if you improve the PRG construction that we'd get, you would essentially be improving the lower bound you currently have. Okay. So to give so one thing is this construction is non-black box, because by definition you are using kind of the way the lower bound is proved in your argument. So let me talk about this technique, and it might seem specific, but it's pretty powerful, and that's one of the main techniques that we have for proving lower bounds.
But is it black box to the extent that whenever shrinkage?
It's almost. You'll see it in a bit. I think it's it's almost, and in every case we tried, we could figure it out. Okay, I'll explain where this almost comes in. So what is shrinkage? Right. So, and there's a very interesting bit of history behind this, because this is where random restrictions first appeared in complexity theory. And I'll tell you where, but let me first define what this means. So you have a class of functions f, right? And we'll say f has shrinkage exponent gamma if the following holds. So before defining it, let me just introduce some notation, which is that of random restrictions. I'm sure all of you know this, but let me just revise it. So a restriction is basically a partial assignment to the variables. So it's a string from 0, 1, and star. And stars will basically correspond to unassigned variables. So if I have a function from n bits to, if I have a Boolean function, then the restriction of f according to rho is just the function which is defined on the starred variables. So this is just f of x, where x I equals y of I if rho I equals star. Okay, so you use the same assignment for same values of 0, 1, where rho is 1 of 0 or 1, and where it is star, you replace y. So this is the restriction. And we'll say a class of functions has shrinkage exponent gamma if the expectation of so we'll look at random restrictions, okay, where the probability that each coordinate is star is p, where p is some parameter. So these we'll call p regular restrictions. I'll define them later, but let me just say rho is a random restriction with bias p, meaning the probability star occurs is p. And we'll say it has shrinkage exponent gamma if the size of f restricted to rho, that is, there is some notion of size. For instance, for circuits, it could just be the size of the circuit, and for other notions, you could define something similar. The expectation is at most p to the gamma times s of f. Okay. So when I apply the restriction, the function shrinks. It has to be a constant gamma. It has to happen for all p. There's some constancy. Okay, so p will depend on n. In fact, so if for all p greater than 0, this holds. Okay, does this make sense? And so why is this concept interesting? Because if you know a family has size gamma, then you immediately get a lower bound of n to the gamma for computing parity under using this function, right? Why is that? Let's see. Because you can set p to be something like let's say 1 over n, right, where n is the number of variables. And then if you apply this to a random restriction with this probability to a parity function, it will be non-constant with high probability or with reasonable probability. On the other hand, when I apply this restriction, the size is going down by n to the gamma. So the size of my original function computing parity better be greater than n to the gamma. Right? So this gives you a lower bound of n to the gamma for computing parity using this concept class. And this is what is kind of implicit in the work of Subotovskaya from 1961. And this is the first place where random restrictions appeared in the literature. And what she showed was that, well, in the modern language, what she showed was that Boolean formulae have, let me abbreviate shrinkage exponent as s dot e from now on. Okay, have shrinkage exponent greater than or equal to 1.5. Okay, and as a corollary, she proved that gave a lower bound for n to the 1.5 lower bound for computing parity. Using formula, yeah.
What does Boolean formula mean?
Yeah, I'll define it. So what's a Boolean formula? It's just basically a formula where the gates are just and or not. You don't allow any other gates. Okay, that's basically a Boolean formula or formula over De Morgan basis. That's what they're traditionally called in the literature. For us, it's just like a formula now. So since this work, I mean, her argument is actually very, very, nice. But you should look it up sometime, how you can get this 1.5 instead of 1. So 1 is kind of always easy in some sense, but because f rho depends on basically p times n number of variables, right? So you should generally gamma equals 1 is possible, is easy to show, but anything greater than 1 is far trickier. Okay, and now let's see what's been done since. So after this work, there was there were no lower bounds for parity. Oh, by the way, getting lower bounds for formula is extremely important because we believe that NC is separate from P. So that means that you should get quasi-polynomial lower bounds for formula for a function in P. Okay, whereas we cannot even separate n squared size formula right now, maybe n cube size formula from all of from even exponential time or something like that. Okay. So let's see. And Kravchenko in 74, I think. Let me get this. I didn't write down the year. Maybe 71 or 74, I don't remember, but so he later improved this using a slightly different argument, but I think if you think about it now, maybe it seems it's kind of the same argument in a different language. He showed an n squared lower bound for parity for formula. So n squared size n squared lower bound for computing parity using formula. Yeah.
This was a shrinkage exponent.
Kravchenko's? It's not exactly a shrinkage exponent, but it's kind of implicit in his argument somewhere that he's showing a shrinkage exponent of. It's kind of a boosted shrinkage exponent argument, but it's implicit. I think it's almost the same. And his argument actually applies for all formulae, not just Boolean formulae. So you can allow any gates in your formula. You can allow parity gates or mod p gates or whatever, but they all have to be constant arity.
With parity gates, you can do it in n size.
you need to have wait. You need to have, even with constantarity, you can have a tree. Okay, so yeah, you're right. So it must be, for Boolean formula, it gets an n squared lower bound. For the other things, it gives a different function which gives the same lower bound. Okay. So this was the status for a long time in terms of lower bounds. I mean, we believe NC is separate from P, so we should really be getting here quasi-polynomial, but we just have like n to 1.5 and n squared here. And Andreev in 1987, basically, as in he gave a very nice kind of unification of all of these things, and he showed that if f has shrinkage exponent gamma, then there exists an explicit function with lower bound of n to the gamma plus 1. Maybe some polylog n terms. Okay. So if you have shrinkage exponent gamma, then he gets n to the gamma plus 1. So as I said earlier, you can easily get a lower bound of n to the gamma immediately by setting p to be this and using the parity function. But Andreev gives a kind of very clever use of the parity function to get this n to the gamma plus 1. And so what this implies is so you get an n to the 2.5 lower bound for Boolean formula. Okay? Yeah? We'll get to that. I mean, for our work, we'll need to do something like this, so we'll in fact construct such explicit restrictions. So all this original work is both in expectation and for fully random restrictions. Okay, so which? It's basically somehow like, uses gives a version of Andreev's argument where gamma is 1. Okay. So this was the status for a long time, and until so people were really interested in the shrinkage exponent. What's the shrinkage exponent Boolean formula of other kind of formula and so on. So from the work of Shubastauskaya, there was no improvement in this 1.5. And until maybe if Russell were here, I won't say this, but as Russell is not here, until the breakthrough of Noam, Nissan, and Russell Impagliazzo, we showed that let's see, this is 94. For Boolean formulae, have shrinkage exponent greater than or equal to 1.5. I think it's 4 here. Okay. I might be getting this, but it's something strictly greater than 1.5. And then this was subsequently kind of simplified and improved by Patterson and Zwick to I think something like 1.56 or something. Maybe I should be more precise. Yeah. Okay. And then came along Hustad, who showed that it is equal to 2. Okay. And this less than or equal to it follows because parity has Boolean formula of size n squared. And that obviously you don't get any shrinkage for parity. Okay. So if you plug this into Andreev's result, you now get the best lower bound for separating P from NC, or any such thing, which is n cubed lower bound for Boolean formula. An explicit n cubed lower bound for a Boolean formula. So as always, like, I'm adding some polylog terms here. Okay. And even here, often, like, you don't get such a clean P to the gamma times SF, but you might get some O tilde factors here. So throughout, just ignore them. It's not important. Okay, and so let's see. And for read one's formulae, something better is known. So Hastad, Rasborough, and Yao in 97 showed that for read once, so these are Boolean formulae where each variable appears at most one time. Have a shrinkage exponent, which is something like 3.27. There's a root 5 here, okay. But they know the exact value. So this is what's known about shrinkage exponent, and these give the best lower bounds we know. Yeah.
The upper bound there something nice.
Uh-oh. Huh. The upper bound is actually, I always wanted to try this. Let's see. There are some technical difficulties. All right. So what was the question? The upper bound basically comes from this simulating majority by read one's formula from Valiant's work. It's the same constant.
And that's tight.
No, the simulating result is not tight, but the restriction thing is tight. I mean, it's probably tight too, but yeah. So, okay, and so, but one thing that's, I mean, all of this is nice, but 87 was a long time ago, and this was the worst case lower bound. So, and we don't even know, we can't improve this n cubed. We can't even make it even mildly average case and anything like that, right? So, what we'll see in this work, if like all of these are not average, not even average case. So we really think we should have very strong lower bounds, but we don't have even mild average case lower bounds. So let me now rephrase this kind of informal statement, which is that if you have shrinkage gamma under pseudo-random restrictions, okay. So you need not just, I mean, shrinkage even under truly random restrictions, but also under pseudo-random restrictions. And one thing that's nice about all these shrinkage lower arguments is that you can make them pseudo-random with some additional arguments. Okay. So this implies PRG with seed length O tilde of S to the 1 over gamma plus 1. So if you want to full size S functions from your class, You can do it with seed length s to the 1 over gamma plus 1. So notice that it basically matches Andreev's worst case lower bound. But this is a completely different function, and I think it's a different proof, and you also get very strong average case lower bound. Okay, so this is the informal statement. So using this generic result, I mean, we can. This is probably interesting. I mean, somewhat interesting by a kind of a black box reduction, but for special cases, you get something concrete, right? Using those things. So, for instance, you get the following theorems, which is like PRG with seed length. Let's see, s to the 1 over 3 plus some little of 1. There are some like annoying little of 1 terms, but just think of them as 0.001 or anything like that. For if you have size s, if you want the full formula of size s, you get lower bound of s to the 1/3 plus little of 1. And the same thing for this is 1, 2 is s to the half plus little of 1 for just formula. Okay, for formulas over arbitrary basis. Gamma equals 1. I mean, in the random case, it's almost trivial, but for the it's not that hard. It's not at all hard. You just need to use some kind of limited independence Chernoff bound. So it's not that complicated. We use the same class of basically the same class. Only for this case, it's a bit tricky, but we can even. I mean, the same thing works for all of these. This is a bit tricky, as you'll see. Probably it should not be so subtle, but at least the current argument is subtle. And you'll get, s to 0.23224 something for read ones. So this is basically using this Hastad-Rasberov-Yau result. Oh, I mean, all these pseudorandom things use the expectation results in a black box way. So use those results in a black box way and then convert them into pseudorandom things. So that's what I meant by almost kind of automatic. Okay, so you don't have to open this block box because like Hastad's result in particular is extreme. I mean, I think it's quite complicated. It's kind of ingenious how we guess this exponent to.
But you need to open it in order to show that it works under pseudorandom.
We don't have to. We don't have to open the box. Okay. And finally, for this gets same s to the half plus little of 1 for branching programs. Okay, so yeah, so here the model of branching programs we consider is arbitrary branching programs. So it doesn't have to be read ones or it doesn't have to be layered. So it's basically just a directed acyclic graph. So you have some graph like this, so on, and each node has a label on it, and there is a start vertex. Right? And each vertex has 2 outgoing edges, one labeled 0, one labeled 1, and so on. This is just a modular branching program we are looking at. And finally, you decide whether or not to accept or reject. So it can be multiple read, it can be oblivious, meaning it doesn't have to be layered and so on. And the size just corresponds to the size of the program. Okay? So in particular, this also gives the average case. Yeah, right. It's strong average case. It's like 1 minus the strong average case, right? So you can basically make it quasi-polynomial or sub-exponential depending on what this little of 1 is. Okay, so, but we'll basically target polynomial is smaller because that's kind of the cleanest case, right? And so what's, I mean, all of the specific things, the previous best was basically seed length, which is omega of n. I mean, it's like previous best had seed something like 1 minus some delta 0 n, even for, so even for linear size circuits or linear size versions of all of these classes, the previous best versions had basically had like very minor gains, something like 0.8 n or 0.9 n. So now we can do square root n or n to the 1/3 and so on. Okay. All right. So that's for the intro. Now let me talk about how to prove this main theorem, right? So as I said, there are two parts in this. So there's a part 1 which says that if you have shrinkage under pseudorandom restrictions, this implies PRG. Okay. So here this is a completely generic reduction. So it does not use anything about the class of functions except something mild, like it's closed under flipping some variables or something trivial like that. So if you have shrinkage under pseudorandom restrictions, then you'll get a PRG, and the seed length of the PRG will depend on how many bits you need to sample from this restriction family. Okay. Well, we thought of, I mean, I won't rule it out, but we didn't say how to make it work. For instance, for AC0, you get amazing shrinkage. Like gamma is like polylog n. Basically, that's what happens for AC. I mean, you can view the switching lemma as giving you something like that. But unfortunately, we couldn't, I mean, our thing doesn't, I mean, we didn't see how to make it work in that regime. But that's a good question, like, whether or not you can make it work for AC0 or something like that. And there is a part 2, which is random restrictions to pseudorandom restrictions. So this is sufficiently general in the sense that you can use all of these shrinkage bounds in a black box manner without looking into their proofs, but it's not exactly generic. So you have to know use some details about the function class, something minimal but some details. Okay, I'll sketch what the proofs of some of these, but I'll mainly concentrate on this. I think this is the main innovative part. Right. It's basically, pseudorandom restrictions will just correspond to a family of restrictions which can be sampled with few bits. Okay, I'll define it. Yeah.
No, for AC0, you mean that part 2 doesn't work?
Part 2 doesn't work, but I don't think that's the only bottleneck yet. There might be a problem even in part 1 because it doesn't go all the way. I don't yet see how to make it work for very, very small, very, very large gamma. And we can see in the argument. All right. So let's talk about part 1, and I'll write up the theorem and post it up here so that push it up there so that this is kind of the main theorem. So for this, first I need some definition, which is, so let's say you have some distribution dp on 0, 1 star to the n. Okay, so where p is some parameter. So we'll say this distribution on restrictions is p regular if each beta's bias, if each beta's probability p of being a star. Okay, but they need not be independent. Okay, and we'll say f has shrinkage exponent gamma, or let's say epsilon shrinkage exponent gamma with respect to pp if the following holds. Okay, is this abbreviation clear? Epsilon shrinkage exponent gamma with respect to the distribution d if the probability under rho of So the original definition of shrinkage was basically said the expected size is small, and now I'm just making it into a high probability statement. And you can afford to lose this log 1 over epsilon because you're going from a high probability statement to a to an expectation statement to a low high probability statement. Okay. So this c can depend. I mean, it's just a constant. It might change, or there might be some hidden log factors, but let's not worry about that. This is the main thing. So the main theorem now says that if so these are the assumptions. Right. So let's say f has epsilon shrinkage exponent gamma with respect to dp. Okay. And this is assumption number 1. Next assumption is dp can be sampled with let's say r of s bits. So I mean, let's look at this definition here, right? So we will want to set p to be 1 over s to the 1 over gamma plus 1. Okay. I mean, this setting basically comes because I want p to the gamma times s to roughly be 1 over p. That's the trade-off you'll get in your proof. And that's what happens even kind of in Andrea's proof. So let's think of gamma being 1, in which case p is basically something like 1 over square root s. Right? So I'm leaving square root s of the variables alive. So for this setting of p, let's say the distribution dp can be sampled with r of s bits. Then can be efficiently sampled.
But what do you efficiently?
I mean, in polynomial time.
No, but do you care about your specific class of prime food? So do you
No,
need
no,
class to be able to sample it?
No, nothing like that. It's just the number of bits you need to be able to efficiently sample from it.
So the goal is at the end to say here the PRG to be completed in polynomial.
Right, exactly. Right. So this simply can be efficiently, meaning polynomial time sampleable. Right. And so this implies there exists a PRG, an efficiently computable PRG with seed basically O tilde of, let's say, log 1 over epsilon. I mean, let's not write that. So wait, let me just say with seed so and so for an error epsilon for size s functions, size less than or equal to s functions. Right. So right, you're right. Let's do times r of s times log 1 over epsilon. Yeah, thanks. Right, r of s will always be polylogarithmic. And if it's not, I mean, it can even be polynomial, like, it can be as bad as this, but let's not worry about that minor thing. Okay. And it's, so as long as you have this, these assumptions, you get a seed length with basically s to the 1 over gamma plus 1. to full size as functions in your class. Okay. And so let's prove this theorem. Let me push that. So the proof is based on, I mean, it's kind of inspired by the Nissan-Zuckerman generator for fooling small space machines. Okay, and so we'll use extractors in our construction. So let me define what an extractor is. So this is definition of extractor. So an extractor is basically a function which maps something like n bits, a long string of length n, and a short seed, and it's supposed to give you something uniform over some input, okay, such that e of x comma y is epsilon close to uniform on, okay, if so whenever the source x has min entropy at least k. Okay, so E is a, let's say, a k comma epsilon extractor if the extractor output is epsilon close to being the uniform distribution on the set of all r bit strings whenever x has min entropy at least k, and y is uniform. And what we will use specifically is some like an extractor which maps, which is n over 2 comma epsilon extractor. Okay, so we'll use this specific setting of parameters. So an extractor which works for entropy half sources, okay, and has d roughly O of log of n over epsilon, okay, and r equals, let's say, n over 4. So it works for entropy half sources. It extracts half of the entropy in truly random fashion, and the seed is basically logarithmic. And we know such extractors exist from the work of Zuckerman from '97. Okay, and since then there have been many improvements, but this is enough for our case. I think you can get polylog here using, I mean, it's not that simple actually. You need to work a lot because you want to extract this constant fraction. So it's not that immediate. And polylog seed, it's not immediate. So Nissan-Zuckerman originally had like polylog seed here, and they had some enter 1 minus something, I think. I'm not sure, but this is the first place where this was constructed. Okay. And all right, so let me now define our generator. I think I'll use a full board for the. So there is no gamma right now. I'm going to choose. Oh, that's an R. Believe me, you're not the first one to point that out about my writing. And all right. Okay. And I think the best way to define the generator is I use a full board. So as you'll see from the proof, I mean, I think once you have it, if you see the generator construction, the analysis is actually almost, it's very short. Kind of the trick is in coming up with the generator. And let me say one word before actually writing it down, which is that, So if you're familiar with this PRGs for small space machines literature like Nissan, Zuckerman, or Nissan and Impaglos and Nissan and Wigderson, all of these results use some kind of communication bottlenecks in computing your functions, and then use extractors to kind of recycle randomness. And shrinkage gives you some kind of communication bottleneck, right? Because if I tell you all the bits which are non-stars, okay, then to compute the function on the bits which are stars, I just need to specify f rho, right? And since the size of this function is small, I just need to communicate a few bits across to the function being performed on the computation being performed on the remaining starred bits. Okay, so we'll basically use this observation in our calculation. So here's the definition of the generator. So we're first going to sample some number of random restrictions independently from our family. Okay. So what does this look like? This is going to give us some strings, like, you know, let's write x1 up till xn here, and you'll have some stars and some bits which are set according to row 1. So this is supposed to be row 1, okay? I mean literally row 1 and row 1. And this is row 2. Okay, so I'm just writing down what these restrictions look like in a matrix form, basically. This is row T. Okay, so we will basically choose T to be roughly something like log of n over epsilon by T. Right? So why do we want to choose T to be this much? Because you want to ensure that every column has a star with high probability. Right? So each each entry is a star with probability P. And across the different columns, these are all independent. So if I choose like log n over p of these, at least one of them should be star with very high probability. Okay, so that's the reason for choosing T to be this much. Now I basically define all of the in some sense all of the bits I need, except for what I'm going to do for the starred bits. Right. So one simple thing to try, the naive thing is to set all of them independently, but that's not going to give you any gain. Right? So what we'll instead do is in some sense like recycle randomness across the settings for these starred bits. So we'll choose x, which is uniformly random from 0, 1 through the n, and remember n is from the extractor thing. We'll choose n in a bit, but let me not specify what it exactly is right now. And we'll choose T different seeds, y1 up till yt, which are uniform in 0, 1 through the d. Okay. So the intuition now is to use E of x comma y1 to set the starred bits in row 1, and E of x comma y2 to set the starred bits in row 2, and so on. So what's the gain here? We're using the single x across all the different t's, and y is very short. Right? So we can take t to be large, and we'll still get some non-trivial gain. I mean, one simple thing that already gives you something non-trivial is to just set the starred bits using this extractor directly. Okay. So the number of starred bits is roughly p times n, right? Because you're choosing a restriction with that much probability being a star. So you expect each row to have roughly p times n number of stars, number of unset variables. Okay. So each restriction has probability p of in each coordinate of being probability in each coordinate of being star is p. Right? So across the different things, it's pn. So if you directly just use an extractor with output length p times n, that would be like the first thing to try. Right? But I mean, it actually works better if you do the following. So what we'll instead do is use this extractor as this extractor output as a seed for a k-wise independent generator. Okay. So let me write it down properly. So let z1 equal this, z2 equal this, and so on. So where gk is generates a k-wise independent string. Okay. So I haven't specified what k is, right? But it just generates a k-wise independent string of length n. Okay. So I basically need the extractor output r to be r equals n over 4 to be something like k times log n. So as long as this as long as the extractor output has length k times log n, I can do this. Right? And I'm just going to use these bits in my stars. And I'm almost done with the definition of the generator, except what I'm going to do at the end, which is to XOR all of these, all the rows. So this is our final generator is equal to this. K is going to be smaller. It will be p to the gamma times n, essentially. Okay. So that's why if to get the full, if you use p times n, you always get seed length square root n. Whereas if you use p to the gamma times n, you get the right thing.
How do you choose in the beginning the restriction results?
Oh, they're from this distribution dp, and they're independent of one another.
Okay, but in terms of cost of seed lengths.
Right. So seed length will be so r of s. R is the number of bits you need to generate dp by p, basically, if you ignore this log, right? Okay, and n will basically be p to the gamma times s, roughly.
Why is it ignoring the log?
Because of this, right? So it's basically r of times t plus n plus d times log of, t times log of n over epsilon for generating the yi's, right? So in the final setting, you'll basically have n to be roughly p to the gamma times s. Okay, and the r of s will be, this is r of s plus over p. So if you balance it out right, you'll set p to be s to the 1 over gamma plus 1. Okay. So
why exactly shrinkage makes all this work?
yeah, so what we'll see basically, yeah, so the intuition is that, so how are we going to prove this, right? So the proof will be the intuition. So, how are we going to prove this? As in any PRG construction, we're going to prove it by hybrid argument. Okay? So let me just set up the notation, and the intuition will become clear. So if you want to prove it by a hybrid argument, so I have to replace each of these things iteratively with a uniform distribution. So let me do that. So let's set zi prime to be some uniform things. Right? So z1 prime is uniform, z2 prime is uniform, up till zt prime. Okay. So let's let u1, u2 up till not use u, but w1, w2 up till wt. Let these be the strings you get in each row when you replace the stars with this z1, okay? Stars with z2 and so on. And let v1 v2 up till vt be the strings that you get when you replace the stars with truly random bits. Okay. So what we'll show is kind of a hybrid argument between the vi's and the z's. Okay. So let's say you've done up till the I steps, and now you're looking at the ith step. So you have vi here.
Oh, so this is why you need a star in every column, so the XOR of vi.
Exactly. Right. That's the point. So if I want to do a hybrid argument, I have to look at this ith column. Right. So everything else is the same except the ith row. So let's look at what's going to happen there, right? So as Srikanth pointed out, XOR of all the vi's is close to the uniform distribution, right? Because T is so large, we'll have a star in at least we'll have a star in every column, and whenever that happens, if you XOR it, you'll get a uniformly random bit. Okay, so it's enough to show that yeah, it's okay. Let me write it down here. So enough to show. So let's fix a function from our function class f, and it's enough to show that probability f of say v1 XOR v2 XOR up till vi minus 1 XOR vi XOR vi plus 1 equals 1 is within epsilon of the same probability where all of these bits are the same. Oh, sorry, this should be wi plus 1. So this is just a hybrid argument. I wrote it formally here. So you have a difference here. That's it. Everything else is the same except in the ith position. Right? So if I show this, I'm basically done. I might increase the error by epsilon times t, but you can just work with a smaller epsilon and everything will go through. So let's look at this row. So what's going to happen, right? As I said, the gain comes because so let's look at what's happening, what we are using for the start bits. I'm recycling randomness from the remaining. But what's the amount of randomness I'm recycling is the amount of randomness needed to describe the function I'm computing. Right? So that's the, So let's define this new function, which is h prime of x. It's basically, so in this argument, we can fix everything except vi and wi. We can consider fixing of that, like that's what you do in a hybrid argument, right? So let's fix that and define f of v1 XOR v2 XOR x, vi minus 1 XOR x XOR, let me not use x, let me use z. Right. Okay. So what I really want to show is that h prime is fooled by like the output of the extractor, right? And in fact, what I really want to study is the h, which is h prime restricted under rho I, right? So what I want to show is that h of zi prime is like epsilon close to h of zi, right? So let's write it in terms of expectation because that's shorter. So I want to show that these two are within epsilon. But what do we know about H, right? So what we know about H is that, so so what's the problem here? The problem is that H depends on X in an implicit way. H depends on Zi, right, through the dependence induced by X and the Vi's. Right? But how much entropy is this dependence costing you? So the entropy loss is, so let's first make some observation. H is independent of rho I and yi. Right? So H is a random function and it is independent of the ith restriction. I mean, it's basically independent. I mean, I'm ignoring some small technicalities, but let's ignore that. Is
H is, just say it's conditional on the restrictions. Like what is it independent?
it's independent of rho I. It depends on the remaining things, but not on rho I.
You find H has been H prime, right?
Oh, sorry. H prime is independent of rho I and yi. Right, you're right.
H prime is H prime.
When I fix everything except the what's happening in the ith,
You don't look at the restriction. Okay.
right? So H prime is independent of rho I and yi. But it depends on X and the remaining rows. That's not a big deal for us. So what does this imply? This says that, because of the restriction property, S of H equals S of H prime restricted to rho I is less than or equal to P to the gamma times S with high probability. I'm ignoring a log again. Okay?
Potentially, so you don't need to resample you can ask the restrictions to be independent because each one has a trade-off symbol.
Right.
Potentially, the symbol is also larger to try to.
Yeah, you could, yeah. That's true. So the point is the dependence of Zi on H is very minimal. The only dependence comes through the description of the function, which is short. And because the function has small size, I can describe the entire function using a very few number of bits. Okay, so this is one property of the size function which we are going to use, right? So with high probability this is true. Let me ignore this log factor, right? So this implies that H can be described with let's call this guy S0 for brevity, with roughly O tilde of S0 bits. It will basically be S0 times log of S0. Okay? So, and H is independent of yi, right? Because yi only appears in the definition of Zi. And X conditioned on H, right? If I give you the function H, whenever this event happens, has mean entropy at least n minus, let's say S0 times log of S0. Let me ignore the log and just say S0, right? Does this make sense? So as I said, the intuition comes from the fact that right, exactly. The function you're computing on the unrestricted bits can be described using very few number of bits.
So is this the first time you're using this shrinkage thing in abstract something to the random?
Well,
Now after explaining it sounds natural, as usual.
yeah.
So this is kind of novel for us.
Yeah, I mean, yeah, I think so, yeah. But this kind of, this using extractor thing is obviously been used before, right? Like in Nissan, yeah.
But I mean the fact that shrinkage corresponds to
Right, exactly.
information.
Yeah. Basically, shrinkage gives you a communication bottleneck too, right? That's the intuition behind this.
Okay, that's what I was going to say. Now we are talking information.
Yeah. So the intuition is that shrinkage gives you a communication bottleneck. So once you have this, you're basically done, right? And let me just set the parameters now. So whenever this happens, we know that Zi is uniform, right? So if I choose, let's say, n to be something bigger, like 10 times S0, right? I'm ignoring log terms, but that's not a big deal. Then I'm basically done. Right?
So it's the output of the extractor that's uniform.
Output of the extractor that is uniform, right? I'm going to choose k to be S0 as well, right? Because I know that this function h I'm computing depends only on as size at most S0. So in particular, it should depend only on S0 variables, right? So I don't need to output a full, fully close to uniform distribution. All I need is something epsilon close to a k-wise independent distribution where k is S0, right? So basically that means I need n to be, so I need k to be S0. So it means I need n to be something like this much, right? So because to generate a k-wise independent string, I need S0 log n bits. Okay, so this is the setting of the parameters. And if you, let's just balance things out and see what the seed length is. Okay. So this implies that generator works. Okay. And the seed length, as is, I mean, we did this before, ignoring log terms, is basically R of S over pli plus the number of bits you need for the extractor, which is S0 times log n. And S0 is basically p to the gamma times S. Right? So you'll to balance this out, you'll set p to be S to the 1 over gamma plus 1, in which case this is just S over 1 over gamma plus 1. Okay? So let me just write this as multiple.
So this gamma plus 1, though, the source of it is completely different from the Andreev gamma.
Yeah. I mean, but it's kind of funny. I mean, I wouldn't say it's completely different because it's the same. But I mean, there could be a deeper connection. I don't know. But from the looks, from the arguments, it seems like it's a completely different place where it's appearing. Okay, so this is part 1. And so for AC0, let's see what happens. So your restriction P will be very small, like P will be polylog, right? 1 over polylog, let's say. And maybe it's the pseudo-random part that breaks down then, yeah. I think this part works, but the pseudo-random part breaks down. So for the pseudo-random part, basically what we'll show is that whenever you have this kind of almost linear shrinkage, like p to the gamma times something, just a simple Chernow bound can de-randomize it. So for AC0, maybe the problem is just in getting a pseudo-random restrictions for which you also have shrinkage. Does it make sense? I mean, so here the seed length depends on R of S, right? So I think it's, we don't know how to do small R of S for AC0. But for all of these things, it works out. Okay, so that's the non-completely generic part. Right? Okay. So let's move to part 2. I think you'd get polylog seed length. Yeah. But I mean, you have to keep in mind that in some sense, we're really trying to beat n to the gamma versus n to the gamma plus 1 here. I mean, so for AC0, maybe because gamma is so large, the difference might be not so noticeable. I think you can, but that won't give you anything. Like, you know, for instance, for the cases where gamma is 1, you get nothing. Right?
It still be non-trivial, right?
For gamma equals 1, it will be trivial.
No, but n to the gamma in general would be.
I think n to, I mean, seed length of s to the 1 over gamma might not be. I mean, you can probably do this using this using part 2, but using something simpler than what we currently do for part 1. But it won't give you anything trivial when gamma is 1. Right?
But you said
Anything non-trivial.
that was not observed, right?
Yeah. I don't know. I don't want to make such claim. Yeah. Okay, so what is part 2? So this is the getting restrictions, getting shrinkage using pseudorandom restrictions part. So let me do like a baby case, and then I'll hint at the complications for the general case. Okay. So the baby case corresponds to shrinkage exponent gamma equals 1. So let's just do like formulae on an arbitrary basis. Okay. So here just you have a formula, and the gates can be any small arity function. Okay. And you want to say that, and basically what we'll show is that you can take dp to be so you are aiming for gamma equals 1, right? So you can basically take p to be something like 1 over square root of s, right? And you can, we'll show that dp equals of log n wise independence works. So you can choose any family of restrictions which is log n wise independent with this bias, though we'll lose some half minus something here. Okay. And why is that? I mean, it's pretty simple, so let's just do it. So you have some formula, right? And let's just look at the leaves. So for formulas, I mean, you can define the size to just be the number of leaves of your formula. It's equivalent up to some polylog factor, so let's just define it as that. Okay. So the size is just the number of leaves. So each leaf has some variable associated with it, x1, x2 up till. Yeah. Okay. Is it up to a factor of 2? Oh yeah, it is a formula, so it has to be out. Yeah. Okay. Yeah. Right. You're right. But some things might be repeated several times. Okay. And what happens when you do a random restriction? Some of these are basically gonna disappear, right? So like, you know, you'll have this guy gone, and so on. And to count the size of the restriction, you basically just want to count the number of leaves. I mean, that's enough of a upper bound for us. Okay. So in particular, what happens is, let's just see. Okay, so let's let ni equal number of times xi appears in f. So let's fix a formula f and let ni be the number of times the variable xi appears in it, right? So what we are interested in is summation I ni times some random indicator random variable yi, where this is indicator of rho I equals star, right? So if the ith variable survives the restriction, then you get size ni, and additively for each of these i's. And we know the expectation of summation of the ni's is s, and the expectation is p times s. So now you just use a Chernoff bound, right? Though you have to be a little bit careful, because, like, you know, sometimes if what if the same variable appears throughout? right? I mean, if it's x1, 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 you don't get shrinkage under high probability, because with some probability it won't be, it will be unset.
P is very small, right?
No, p is, it's not polynomially small. You want really small error, right? So you want polynomially small error, whereas p is basically 1 over root n.
So epsilon is equal to 0.
Right, you want epsilon to be one polynomially small. But you can get around this minor technicality by looking at like some kind of heavy variables and tail light variables, and this is, that's fairly standard stuff. Okay.
So then you don't really get this.
So basically you get seed length to be, that's why it's, well, s to the half plus lit law of 1.
Anyway, you're not going to, it's a reasonably good probability. You have one variable at the level, it's never going to be true.
Right, but the point is, if it appears, then to show shrinkage, you can just replace it with a small size formula. So that's how you handle it. Right, because the formula says that matters and not just this. Right. So that's a minor technicality. I mean, like, you know, just do kind of heavy variables and light variables, and do some kind of enumeration over the heavy variables. For the heavy variables, we'll just use size bound 2 to the number of heavy variables and so on. Okay, so I don't want to go into that. What's interesting is what happens for De Morgan basis when gamma is not 1. So the same thing works for even for branching programs. When it's the same, whenever gamma is 1 is very, I think it's fairly straightforward to get a de-randomized version. Okay. So now the question is handling gamma greater than 1, right? So the point is, the way you show this gamma greater than 1 is you really use some kind of correlated way in which the entire things disappear. You cannot just use a union bond across the different parts, right? For instance, Subatovska's argument is extremely elegant. What she said was, let's look at any Boolean formula, right? And let's look at a gate which has 2 leaves. I mean, this I don't need this, but I just want to tell you because it's so nice. So this is, let's say, an AND function, and have 2 leaves x1 and x2. And if I consider restriction, then each time x1 disappears, right? I mean, when it's set, it will make x2 also disappear with probability half. So instead of just getting a linear, I mean, like, you know, going from 1, you're getting expected disappearance of 1.5. And that's what translates to this shrinkage exponent of 1.5. So that's how she shows it. But now if you look at these things, how are you going to make all of this these correlations? How are you going to use it in a non-trivial way, in a pseudo-random thing? Well, what we'll do is the following. I mean, for the general De Morgan basis, again, there is you run into a lot more difficulties. But let me just talk about read once Boolean formula. Okay, so I'll describe this analysis, and then I'll hint what happens for the general case. So here you can do something similar like heavy and light variables, but you run into a lot more complications. And unfortunately, we need some kind of very subtle conditioning and so on. So, but let me just talk about this guy. Okay. So the idea is you have this big formula which is read once, and what we'll do is let's think of the complete binary tree for now. Okay. What we'll do is we'll kind of group this, split this into big pieces. Okay, and so the technical claim is we'll split this into big pieces of size like less than or equal to L. I mean, not too big pieces, sorry. Okay, not too many and not too big pieces. Okay, and then we'll use some, and let's say a decompose F into L subformulas, right? Sorry, into something like O of n over L. Let me just state the formal theorem. Right. So the claim is that can decompose F into O of S over L subformulas. So S is the size, okay, of size less than or equal to L each, okay, but with one catch. So each subformula has less than or equal to 2 special variables. So what do I mean by this? So in case of complete binary tree, the point is I want to divide into this small piece, this not too large pieces. And if I do this and I use an L-wise independent random restriction, right, okay, then I can use the original argument in a black box way, right? Because when I use an L-wise independent random restriction, I know that each of these guys shrinks to size p to the gamma times the size of this, right? And let's call this subformulas G, G1 up to so on, right? And I'm just going to use a Chernoff bond across all of these guys, okay? Because these are all read ones and these are independent of, I mean, these are not exactly independent, but you need, like, as long as you have log n wise independence, you will get it, okay? But what's tricky is how, I mean, this is for the complete binary tree. But what do I do if it's something, if my formula is something like this? Right? So I cannot get such a nice decomposition here. But what we'll instead do is kind of decompose it into these formulas. And so on. So these formulas are no longer independent of one another, but the output of one feeds into the other formulas. But we can control this kind of feedback by saying that each subformula depends on basically at most 2 other subformulas. Okay? And this is easy to show. It's just some kind of inductive decomposition, something like this, exactly this. Okay? So let's call these subformulas G1 up till G L, right? And we want to relate the shrinkage of F to the shrinkage of the GIs. So my claim is we are basically done because so we should basically be done because we know that S of F restricted to rho is less than or equal to summation of S of F of GI restricted to rho. But it's not exactly true, right? Because I have the special variables which are not like, you're not doing any simple restriction on them. You don't know what's happening there. What's the disappearance probability? We don't know. But we'll do kind of the worst case analysis and say that work with restrictions where special variables are always stars. And it's kind of the worst case that can happen for you. I don't know when these are going to disappear, but I'm saying, okay, let's forget about that. Let's always just keep them as stars. And the point is, if I have a big formula and I'm trying to study a shrinkage, if I fix 2 specific variables to be stars, it should not change my shrinkage too much, right? So that's what we're going to do. So we'll say it's less than or equal to S of GI of rho prime, and then we'll kind of hand wave and say this is basically the same as just under a random restriction for GI, but GI has size at most L. And our rho is L-wise independent, right?
So you're using size for 2 things, right? One thing you're using size to say dependent on most S variables, so you're pulled by S-wise independence.
Mm-hmm.
And the other one was that you can discover it roughly.
Right, that's the one. Those are made to just the 2.
Potentially for more complicated models, those are not
Right, right. I mean, this assumption that you can describe it with S log S, that's a very strong, I mean, yeah, that's a strong assumption. Right.
I think AC0, right? They are totally different.
AC0 also it is true if you just,
AC0, if the one hand you can describe it, let's say for size AC0 can describe it for many bits, but you can put by for log, right? So the big
yeah. Right, in fact, we thought about that a lot, like, whether or not, for instance, I erased the definition of the generator, but instead of generating a k-vaz independent string, I can kind of recurse probably, right? And that will be one of the open problems I'm going to talk about at the end. So this is what we have, and this implies that expectation of S of f rho is, let's say I just want to bound the expectation, then I can just use a union bound, right? Okay, and each of these becomes basically p to the gamma times L, right? Because it's like a truly random restriction on this part, and hence you'll get that. But to get a large deviation bound, you have to be for read one's case it's easy, right? Because again you'll say let's define these as your random variables yi. These are basically control and they are log n wise independent, and hence you get the same Chernow bound as you had before. So this is kind of the sketch. I mean, almost the complete proof except for this part. How do you go from rho prime to rho? Okay, so I'm saying, like, I know a shrinkage under a full random restriction, but now I'm asking you to never set a specific variable. I mean, it's not that clear, right? Because here, for instance, x1 can like really contribute a lot to the expectation.
Just take the original formula. Let's say one variable is special, right? So I'm never going to query it. It's going to query the second. It's going to have this twice size formula.
If you right, but that's gonna so it works for the expectation calculation. Okay, what you're saying is right. So if I don't query this guy, like for instance, let's say I just want to use the black box statement that the expectation is small, right? And I know that this guy disappears, like makes it disappear all the time. So then all of the contribution to the expectation is coming from this special variable being unset.
But you don't know there's a specific formula, and not all formulas in the same class.
Right.
So this class should be closed or something like.
So that's what you want to do, but it's not immediate. So what you really want to do, what you're saying is basically this. So why not let's start? I mean, I'm making this to be star. So I'll do something like this. I'll replace this with some small formula. Okay, small formula that never gets set. Okay, so if I do a random restriction, it never gets fixed to a constant. Let's say I know this. Then what you're saying will work, right? So I will increase the size a little bit, right? And the behavior of this formula under random restriction is close to saying that this guy is always star, because this guy is never disappears on itself. Right? Does it make sense? I'm saying whenever you have this variable that you're never going to set, let's replace it with a formula, with a fixed formula, which never like the parity function, which never disappears under random restrictions. There is no way you can avoid. At least we didn't find a way to avoid it.
This will blow up your formula size by polynomial.
Right. So I mean, you can. The point is, you have to work with this probabilities being small. This causes additional complications, but you can make it work too. Formulas which output 1 bit, but
Let's say what's special is a pair of formulas, one which outputs a value which is big as 0, and the other one which outputs a value which is 1. Right? Now you have these two formulas, and obviously the size of the formula is the maximum, but let's run by the sum. once you have the sum, then each one of them is a formula where this variable is.
But think about the expectation bounds you're trying to use, right? So they really use this kind of correlation that whenever x1 disappears, you're going to get a big loss. So if you look at the proof, they really exploit this kind of structure.
Right. But here, take a formula.
Mhm.
There's one special variable.
Right.
Think of this. Replace this formula with two formulas. One with this variable is set to 0, and one with set to 1.
Okay.
You can always compute your original formula by the output of those two plus squaring your new variable. The sum of those plus
Mhm.
1.
Right.
But then definitely you can say that now you can just for each one of those it gives you really play around with restriction.
Mhm.
So those shrink by a lot. Just by sometimes a class. So different formulas of the same class. And now the original thing will tell this plus 1.
I see what you're saying, but I'm just saying that the loss in expectation might just come from the first formula disappearing completely.
In this case, it will come but just by each one of those will be much smaller.
So let's think of this case, right? So you have one variable at the top, and you have like a long chain, which just computes the parity. And we want it to work for all p, right? Let's take a constant p, let's say half or something. So the expectation in disappearance will just come from this guy. With probability half, I'm going to lose size n.
That's fine. Now replace this by two formulas.
Okay.
One with this variable is equal to 0 and one with it to 1.
Mm-hmm.
And one of them you get this, and now when you get zero size formula, right?
Right. So how do you argue about this zero size formula is what my question. So you want to rule. So you want to make it work in a black box fashion. So
So you don't. You use a factor of 4 then at the start. What do you show?
you don't lose a factor of 2. So let's just compute this expectation, right? So you have the size n here, okay, and I'm looking at the random restriction. So you're saying let's work with 0 here, and let's work with 1 here, right?
Each one of the size at most s.
Right, size at most s.
So after the restriction, we have s times p to the gamma, each one of them.
No, here the shrinkage basically because it's 0.
I don't care, but it's still bounded by s. It's computed by something smaller. But
Right, it could be bounded by s, right?
But still under the restriction at most s times p to the gamma.
Mm-hmm.
It's smaller, but still an upper bound. And same for the second one.
Not for the second one.
It is, because it is a formula.
It's
It's a formula of size s in your same family.
think about this using the same argument for this for Subotovskaya's argument.
No, but the point is, okay, we assume that your family is closed under setting variables to values. Like if your formula on the right there is still from the same class.
It is from the same class, but now you have to really use the fact that you're setting one bit. So it's not just s times p to the gamma, but p to the gamma times s minus 1. So you have to use that to bootstrap the whole thing. I mean, we can talk about this offline, but let's think about Subotovskaya's argument, right? So the fact that you disappear both of them at 1 in one shot is what gives you this gain over 1. And now you're kind of basically ignoring that. You're using a union bound across the two things. And we don't know where this is happening. It can happen at the very top or at the very end. I mean, you lose more than that. We tried this and it did not work, but we can talk about it offline. Okay. I mean, it'd be great if it works, but unfortunately, when we tried this, it did not work in a black box manner. Okay. And there's a simple fix for it, which is to replace this with a formula of some small size, which never disappears. And we know such formulas exist by standard stuff in complexity.
It's just a parity formula.
Well, for parity, it works for most cases. For read ones, you have to be a little bit careful.
Oh.
For read ones, you can use majority or something like that.
But how large is the formula that you put in there? It has to be pretty big, right? It has to be like size 1 over p or something.
Right. So there's a way to bootstrap all of this. So this fix I suggested works for small p. For large p, what you'll do is, so this basically appears in the general case when it's not even read once. So you face the same problem there. And let me just say a word about it. And I mean, I don't have time to go into the details. But what we'll view it as, we'll say p, write p as some q to the r, right? Where p is polynomially small. It's like 1 over n to the 10, let's say. And q is not too small. It's like 1 over root n. but R is 20. So you're doing it in rounds. So you're using you can view a random restriction with bias P as applying R rounds of restrictions with bias Q. And for each bias Q, you use a log n wise independent restriction. So it's kind of a composition of log n wise independent restrictions using independence. So that's the final restriction family we use. Okay. So let me finish with a couple of open problems. So the first open problem is, can you make it work for which one? Okay, per request. So open problem 1 is basically whether or not you can recurse. So as Shahar pointed out, and this is something that happens even in the Nissan-Zuckerman generator, is you don't need, you can use the extractor output to as a seed for a PRG which fools things of that size, right? And hopefully get some non-trivial gains from that. But unfortunately for us, the bottleneck comes from not from the output of the extractor, but from the entropy loss. So you're always losing this S0 bits of entropy, and so n has to be at least S0. So we could not make it work because of that. But if you can recurse, that'd be amazing because you can improve even the worst case lower bound. Improving n cubed lower bound would be earth shattering. And problem 2 is, can you make it work for AC0 and so on? Okay, and here once again, I think the problem is with part 2.
No, but again, the entropy loss, I don't see how are you going to describe a decision tree of height log n using a few things? If you're aiming for error inverse polynomial, you'll have to allow the decision tree to become depth log n.
Right, let's see. So you're saying the entropy loss might be too much. No, if you're allowing polynomially smaller, see for us we can allow P to be, no, you still need depth log n, right?
Yeah, if you make P very small, then you lose in the other part again.
Right. So you can probably get like any polynomially small seed length using this approach. But I'm not sure. There might be a fix for that. I think the bigger bottleneck is part 2. There might be problems even in part 1, but I think the bigger bottleneck is part 2. Like as I said, the part 1, like basically it comes because I want to go from gamma to gamma plus 1. Right. All right, and
Maybe if you want to recurse, of course, definitely let's simplify part 1 to gamma and then see if this could recurse.
oh, that I don't think there's any hope for recursion there. I mean, then it basically the generator just becomes trivial. Kind of, I mean, the whole complication just comes from part 2 somehow. And I mean, you really want to exploit this extractor thing in a subtle way, I think. You might succeed, but my suspicion is that you have to use this extractor framework because extractors are it's a very powerful tool we are using in there. Like that's what happens in the Nissan-Zuckerman construction. Well, parity, you know that n squared is best.
You need complicated functions.
Right, exactly. Yeah. I don't know what's the best known simulation for Andreas function. Do you know if Andreas function can be computed in size? I'm not sure, but it might be. It's basically like a parity. So.
In general, it's gamma plus 1 the right answer, or is this?
Oh, I mean, it should not. Oh, for shrinkage, you mean? If you want like a black box, maybe? It will be very difficult to say. I mean, you have to.
For one of these models, do we know it's not?
No, I mean that's what I mean. It'll be difficult to say, right? Like you have to like it'll be. I mean, to even formalize that question might be difficult. Okay. Any other questions?